Today we are going to be solving this problem using the method of double integration. This problem says determine the equations of elastic curve for the beam using x1 and x2 coordinates. Specify the slope at A and the maximum deflection EI. Okay, so this problem is going to be a bit long, but pay attention the explanation until the end. Okay, so here we have the reactions. We have B. I'm going to put the reaction BY. We have at point A is a pin, so we have the reaction AY, and we have the reaction AX. We have no force at the X direction, so therefore we have AX is going to be 0. And then to get the other two forces, AY and BX, we have to take the moment either at point A or point B. In this case, we are going to take the moment at point A. So we do the summation of the moments at A is going to be equal to 0. Counterclockwise is going to be positive. The first force that we have is P, and the distance between P and the location A is going to be this low caps A. So we have, and this is going to be a negative moment because the rotation is going to be clockwise. So we have P times A. Then we go to the second, and this one, the distance between this P and A is going to be basically L minus A. So we have here minus P, and the distance is L minus A. And finally we have BY, in this case is going to be positive, so we have BY times the distance L, and everything here is equal to 0. In this case we need to do this calculation, so we do negative PA. We solve this equation. We have negative PL, and then you have negative with negative becomes positive, so positive P times A plus BY times L equal to 0. If you see here, we have negative PA with positive PA, they are going to cancel out, and therefore we only have PL with BL. So if you rearrange this equation, we are going to have negative PL plus BYL equal to 0, and this is going to give us BY. Here we can cancel out L with L, so we have basically BY is going to be equal to P, and so we have the reaction at this point. And if BY is equal to P, to find the other reaction, we do the summation of the forces in the Y direction equal to 0. Going up, in must positive direction. For this one, we have AY, then we have negative P, and then we have negative P again, and then we have plus BY. This is equal to 0, but we know already that BY is equal to P, and therefore if you do this calculation here, we have AY, this is going to be P minus P, they are going to cancel out. Okay, so this P here is going to cancel out with this P, so we only have one P left, and obviously AY has to be equal to P as well as a B. It shows that this problem is symmetrical. Okay, so it's going to be easier to calculate. Now, in order to do the double integration, we have to remember the equation for double integration, and the equation for it is the following. We have EI, okay, the derivative d to v, and v means the deflection, and we have the dx square, and this is going to be the distance that we have. This is equal to the moment, in this case moment with x. Okay, it varies with the x. And then after we get the moment for each section for x1 and x2, we are going to take integrals, which is the inverse of the derivative, and then we're going to get the both the deflection and also the deflection and the displacement. Okay, so in this case here, let's start with x1. So x1, as you can see here, it goes until point B. So we are going to make a cut. Okay, and this cut has to be between the point A and the force P. So I'm going to make a cut somewhere here, and then when you make a cut, let me try to draw something here. real quick. So here we have the pin, we have this beam, we have the force P here. We are going to make a cut before the force P, okay? Here was the force P. Our cut is before the force P. And once we have the cut, we only see, let me take the red, we only see the reaction force, which is P, and the distance between the cut and this force is going to be our x1. That's basically what is here. So because we are cutting before P, we cannot see anything beyond the cut, and we are going to basically ignore what we have after the cut. And since we did that, when we place a cut, we're going to see the internal forces, and here we have the moment, which I'm going to call M1. We also have the shear and the axial forces, which I'm not going to draw because there is no need. So based on this, we have to calculate the moment M1. And what we do the summation of the moments at the cut. So we do the summation of the moments at the cut is equal to 0, because the internal moment at the beam has to be 0 when we place a cut. We are going to follow the same sign convention, so counterclockwise is positive. And once we make the cut, we have this M1, which is going counterclockwise. So we have here M1. And then we have this P force goes clockwise, so we have negative P, and the distance is x1, and this is equal to 0. If you rearrange, we have our M1 is equal to P times x1, okay? So that's the equation that we are going to start with. And having this equation, we can replace through the double integration equation, which is this one right here, because we have the moment. So here we have, let me just go here. Okay, so here we have EI, we have D2, and D is going to be V1 dx1 squared equal to the moment M1, and the moment is going to be P times x1. Okay, so this is the second derivative, but we want to see the deflection, which is basically the displacement over the distance. In that case, we have to take an integral right here. And then if I take an integral, I'm going to take an integral on this side and also take an integral on this side here. And then if you take the integral on both sides, what's going to happen is, if you take the integral on the left side, this is a constant EI, so you're going to keep the EI here, and this is going to become dV1 over dx1. And for those of you who are not familiar with this notation, this basically means your deflection, okay? So this is also, I'm gonna see in books as theta. This means your deflection, your rotation, actually, not deflection, sorry, is your rotation. And then in the other side, if you take the integral of P is also a constant, x1 is the only variable here. So in this case, we have P is repeated, and you have x1 is squared over 2 when you take an integral, plus a constant, which we're going to call C1. But then if you take an integral again, and we are going to take an integral again because we want to see the displacement, which is the V1, out of this derivative. If you take another integral, we are going to end up with the following equation, EI. In this case, we don't have the derivative anymore, it's just V1 equal, and when you take the integral in the right side, we have P x1, now it's going to be to the third over, and then drops a 3, right? So 3 times 2 is going to be 6, plus C1 x1 plus C2, we have to add another constant, okay? So this was our calculation for our x1. So I'm going to label here, it's going to be easier to work with later. So this is our equation 1, and this is our equation number 2. Now, I'm going to just, split the screen a little bit here. Let's do a similar calculation, but now using x2. And as you guys can see, x2 is a x that goes after P, okay? So it goes beyond P and forward. So in this case, we are going to make a cut that is after P. And if I do a similar drawing like this one, I have our pin, which is point A, I have the beam, we have the point P, but now we are making the cut after P. So P now is going to be part of our equation and also the reaction, which is P at this point. And this cut now I'm going to call M2, right? Because we're dealing with X2. We know based on our initial design that the distance between the location A and P is low caps A. So this distance here is going to be A. And the distance between the initial point and the cut is going to be X2. And I'm going to call this small distance here B, okay? Just to make our calculations easier. We are going to need this later. Now, we need to calculate, as well as we did for M1, we need to calculate M2. And to calculate M2, what we are going to do here is do a moment with respect to the cut. So we do the summation of the moment at the cut is equal to 0. Again, going counterclockwise is positive. So if you do a moment with respect to the cut, we have M2 is our first unknown. And then we have the force times the distance B, right? Because this is the distance. In this case, it's going to be positive P times B. And then here we have not the P, but this going counterclockwise, so it's negative P times X2. B is a unknown that I just gave in the problem, okay, because it was not given to us. So let's get B in terms of A. And this is a very easy change here. So I'm going to put, this is very easy. We know that A plus B is equal to X2, right? A plus B is equal to X2. And therefore, B is going to be equal to X2 minus A. And then I'll come here, instead of B, I'm going to put X2 minus A. And now we can do our calculation so we can find our M2. And M2 here is going to be M2 is equal to, actually let me not put the equal sign, but the actual summation. So we do P times X2, so we have P X2, P times A, and this is going to be negative, so it's going to be negative PA. And then here we have negative P X2, and this is equal to 0. As you can see, px2, positive, negative, they're going to cancel out. So we are going to end up P2 equal to PA. So if you rearrange here, we have M2 is equal to PA. We have our second moment now with respect to the X2. And now having the second moment, we are going to do a similar calculation that we did here. Okay, but now we are going to calculate only for X2, and then we do EI dV2 now over dx2 square is equal to our moment, which is PA. And here we are going to take an integral as well as we did in the previous one. And then if you take an integral for this one here, let me just write to the side. If you take an integral to this one, we are going to have EI dV2 over dx2 equal to PA x2, because we didn't have any variable here at the beginning, plus another constant. We already had C1, C2. Now I'm going to do a constant C3. And this is going to be my fourth equation. I'm going to put actually the third. And now I'm going to do one more integral. Now take an integral for this equation. So if I do an integral for this one, I'm going to end up with the following. EI now is just V2 is going to be equal to PA x2 squared over 2 plus C3 x2 plus another constant C4, and this is going to be our fourth equation. So we have 1, 2, 3, 4 equations, and then we need basically 4 boundary conditions to solve this problem. And for boundary conditions, we are going to use the first one. We're going to look in the problem and we see that there is no displacement at A, right? at A, the beam cannot displace as we have a reaction point here. And this is going to be our first boundary condition. So I'm going to call here boundary conditions. The first one is for x1 equal to 0, the v1, which is our displacement at the beginning, is also going to be at 0. And the equation that we are going to use to work with it is the equation number 2, because we have displacement and also we have x. So if you look at this equation, I'm going to rewrite here. This is our first boundary condition. In this one, we are going to have EI and v1. Here we have p x1 to the cube over 6 plus c1 x1 plus c2. But we know that v1 is going to be 0, x1 is 0, and x1 is 0. So therefore, if you look at everything is 0, which means that our c2 is going to be equal to 0. So we were able to find our first constant, c2 is equal to 0. Now, the second is a bit tricky, but as I said in the beginning, if you look at based on our reactions and based on how it looks, this problem is symmetrical problem, means that you can flip and it's going to still be the same. And what I'm saying by that is when you have the deflection here, it should be something like this. Okay? And by this, I mean that at a midpoint, I try here the midpoint, I have my maximum deflection. And every time you have your maximum deflection, it means your rotation, your theta, is equal to 0. Okay? So this is some tricky part of this problem. That's why I'm solving it. And then by this, with respect to this location, we are going to be dealing with x2. And then we also are going to consider the slope of x2 at the midpoint. And this is going to be our third equation, because our third equation deals with the slope, right? Like I told you guys, this is the slope, okay? So the slope is going to be 0 at the location in which x is going to be what? L over 2 is at midpoint. So this is going to be our second boundary condition. And this boundary condition here, we have that for x2 equals to L over 2 is at midpoint, our rotation theta is equal to 0. Okay? And now we are going to rewrite this equation right here. And we're going to do all these calculations. So we do EI dv2 over dx2, which is our theta, is going to be equal to PA x2 plus C3. And then we know this is based on our boundary condition, this is equal to 0, okay? And our x2 is going to be now L over 2. So we can rearrange this equation so we can find C3. So we are going to end up with 0 is equal to PA L over 2 plus C3. And then if you rearrange and solve it, you're going to find that C3 is equal to negative PA L over 2. So we just found the second boundary conditions. We still have two left, which is a C4 and C1. Now, based on our problem, if you look at here, although x2, we are using x2 to analyze the beam between this P and this P, and x1 between the reaction point and the P, when they meet, and the location that they are going to meet is going to be right here below point P, both x1 and x2, they are going to be valid up to this point. And therefore, when they get to this point, if both equations get to this point, they have to have the same slope theta and the same displacement. And this is what we call continuity equations, okay? So that's going to be used for finding the two constants left. So we call here CC, it's continuity equation. Actually, I'm going to put, yes, CC. Here we have that for x1 and x2 equal to a, so x1 equals to x2 equal to a, this is going to imply that theta 1 has to be equal to theta 2, as well as v1 has to be equal to v2. So we have two equations here and we have two unknowns left, and therefore we are going to be able to solve this problem. Okay, so here we are going to make this equation 1 equal to equation 3 and equation 2 equal to equation 4. So for the first one, we have px1 over 2. Let's write here. So this is going to be 3 p. Instead of putting the x, okay, I'm going to put the value of a, because we have x1 equal x2 equal to a. So this is going to be pa squared over 2, pa squared over 2 plus c1, and this has to be equal to the equation for the slope for the x2. So we have pa, so it's gonna be pa squared, pa squared plus c3 plus c3. Okay, and we know c3 already is this one here, so I'm gonna actually delete this and actually put the c3 value, which is negative PAL over 2. So let's just calculate this and we can rearrange, so we can have the value of C1, and C1 here is going to be, if you solve this, just send this to the other side to subtract, and this is going to be PA squared over 2 minus PAL over 2. So this is the value of C1, okay? Because we cannot do much here. If you still want to rewrite in a better form, this is the same thing here. We can write, let me just get the pen. We can write C1 is equal to PA over 2, and this is going to be A minus L. This is another form of writing the same equation right here. Okay, but here we just use one of the continuity equation, which was theta equal theta. We have the second one, which is the displacement equal to displacement, and then is equal to the second equation has to be equal to the fourth. So we have px1, actually I'm going to replace x by a, so we have pa, this is to the cube, over 3, actually is over 6, plus c1 x1, and we guys can see that c1 is this big number here, right? So we're gonna place it pa squared over 2 minus pal over 2, and everything is multiplied by x1, which we are assuming x1 to be a, and then we have c2, and c2 is 0, so I don't need to place it here, and this has to be equal to the second part of our equation, which is pa x2 squared. A is going to be here, so it's going to be pa cubed over 2 plus c3 just calculated here is negative pal, so negative pal over 2, and this is time x2, which is also a, and plus c4, and that's the unknown that we are trying to find here. Okay, so here we can do the calculations and we can find c4. So we have pa cubed over 6 plus, we're going to multiply a by everything here, so we have pa cubed over 2 minus pa squared l over 2, and this is going to be equal to pa cubed over 2 minus pa squared l over 2 plus c4. And then if you look it closely, we have pa squared l over 2, and here we also have pa squared l over 2, the same sign, so they are going to cancel out. We also have pa cubed over 2, pa cubed over 2, so they are also going to cancel out, and therefore now we have c4 equal to pa cubed over 6 PA cubed over 6. So this is basically our fourth unknown constant. So we have constant C2, C3, C1, and C4. We have all four unknowns. And here's the equations, equation 1, 2, 3, and 4. And basically we are almost done. The problem is asking us to calculate the equations of the elastic curve for the beam using x1 and x2. And the equations are those one here. We just need to replace the C1, C2, C3, and C4 by the results that we calculated here. And another part is says to specify the slope at A and the maximum deflection. Okay, so the slope at A, basically we are going to use the x1, right? Because the equation that we are dealing in this range between this point A and the force P. So to find the slope at A, we are just going to take the x1 and make it equal to 0 because this point. And for this one, we are going to use the equation 1, okay? So let me write it here, is slope at A is going to be the first equation here. We have EI, and then we have this. I'm going to replace this dv1 dx1 by theta. So we have theta A is going to be equal to px1 squared over 2, px1 squared over 2 plus c1 and c1 is here, actually is here, pa squared over 2 minus pal over 2. And for this one, we know that we are calculating at the x equal to 0, so x equal to 0, this term goes to 0, and so we only have this equation left. And as I told you, we also can have C1 written as PA over 2A minus L. So we have here EI theta A equals to PA over 2A minus L. And then if we just want to find theta A, we just need to do cross multiplication. And we are going to find that theta A is equal to PA over 2EI times A minus L. Okay, so this is going to be the theta A, one of the answers for the problem. And the final answer that we have left is the maximum deflection. And like I told you guys before, the deflection is going to happen something like this, and the maximum is going to happen at the very middle point. And for the middle point here, we are going to be dealing with x2, right? Because x2, we are working in the range beyond point P. So for this one, we just need to use the deflection equation for x2 and make x equal to L over 2. So this is going to be the equation 4. I'm going to write here max V. For this one, we have these equations: EI V2 equals to PA x2 squared over 2 x2 squared over 2, and then we have C3 x2 plus C3 x2 plus C4. Now we have to replace C4 is PA3 over 6, and C3 we calculated before is negative PAL over 2. It's going to be PAL over 2. So let's just replace it, and then we have EI V2. Here we have PA, the location is going to be a midpoint, so my x is going to be L over 2 squared over 2 plus at this one we have PAL over 2, and the location again is L over 2 plus the final one here, this is PA cubed over 6. Just one thing, this C3 is negative, okay, so I forgot to put a negative sign here. And in this case, this is going to be a negative sign right here. So if we finish this calculation, we have EI V2 is equal, if you calculate this, you have PA L square, 2 square is going to be 4, 4 times 2 is going to be 8. We have negative here, PA L square over 4 plus PA 3 over 6. Now the common term between all these is PA, PA, PA. So if you just wanted to rearrange here, and also the common division number for all these is going to be 24, right? So if you just want to rearrange this equation, what we can do is replacing these numbers, and we have, actually, let me just write it. This one here is going to be 24, gonna be 3 here, PA L square over 24 minus the second is going to be 6 PA L square over 24 plus 4 PA cube over 24. Okay, so if you want to rearrange and find a V2, which is the displacement, you have V2 is equal to, we have PA, you can see that this is 3PA L square and also PA square the same, so we can subtract 3 minus 6, this is going to be negative 3. Okay, so here we have PA over 24 EI, and we're going to multiply negative. If you have already PA, these only have left negative L square, and for the other one, let me just rearrange this. If you have this 3L square minus 6L square is going to be negative 3L square, and you have PA, and this is PA cube, so it's going to be positive 4A square. If you just want to rearrange to look it better, we have V2 is equal PA over 24 EI, and here we have 4 A square minus 3L square, and that's going to be the maximum displacement, which is also the displacement for V2 at the midpoint. Okay, so here we have finished this problem. It was a bit long, but I hope you guys have followed. Thanks for watching, and I see you guys in the next solution video. Okay.